welcome to today's class. Today we are going to speak about the Poincaré Disc. We're going to see that several properties are going to be easily deduced from the fact that their counterparts in the hyperboloid and in the upper half plane have already been proved. So recall that we already introduced the Poincaré Disc as the unit disk with certain Riemannian metric, which is not the usual Euclidean metric, but rather the one obtained from the Minkowski metric on the hyperboloid through the stereographic projection from the point 0, 0, minus 1. Right? So here is the picture. So recall that we defined this diffeomorphism between the open unit disk and the upper sheet of the hyperboloid. And through this diffeomorphism, we pulled the Minkowski's form, which on M is a Riemannian metric. And we obtained a Riemannian metric for D, right? So the explicit formula for this diffeomorphism you can see here. And then we saw, and we left it as an exercise, that when you compute explicitly the formula for this Riemannian metric so defined for the open unit disk, the explicit formula is given by this, right? So that at any given point, the inner product of two tangent vectors is a positive multiple of the usual inner product, where this positive multiple varies with W, right? And then and actually becomes very large when W is close to the unit circle, right? So the closer you are to the unit circle, the bigger a vector becomes, right? The larger a vector becomes. Okay, so we already saw that. Okay, we also saw that certain Mobius transformation, namely the Cayley transformation, gives us a bijection, and actually a biholomorphism between the upper half plane and the disk, right? And this is how we gave the upper half plane certain Riemannian metric, right? We actually pulled this Riemannian metric to the upper half plane through this Mobius transformation, right? And somehow the behavior, the basic behavior of the Cayley transformation can be seen like this. So -1 is sent to I, 0 is sent to -1, 1 is sent to -I, right? So somehow if you go this way, here you go this way, actually. And actually it can be seen very easily that infinity, that the point at infinity, which is in our bar, goes to 1, right? So, and this is just because it's this one divided by this one, right? So, okay. So the point at infinity goes to 1. So you see, in particular, for instance, the positive part of the imaginary axis goes to this segment, to the open interval -1, 1, for instance. We saw that. Okay. So now let's show kind of some analogs from theorems we proved for the upper half plane and for the hyperboloid. So let's start by showing that every Mobius transformation which preserves D is actually an orientation preserving isometry of the Poincaré Disc, right? That is of the unit disk with this Riemannian metric. Which, by the way, we know which matrices in SL2Z give us such Mobius transformations, right? Namely, the matrices in SU11. for which we gave a very explicit description. Right? It's the set of all matrices of the form alpha beta beta conjugate alpha conjugate with determinant equal to 1. Right? Okay, let us show also, like now that we have computed kind of completely the Riemannian isometry group of the upper half plane, let us take advantage of that to show actually that this way we obtain all possible orientation-preserving Riemannian isometries of the Poincare disk, right? So that all of them are of that form, all are of this form. Which of course is going to have this fact as a consequence, right? That as a consequence, all this means that we will have computed the group of orientation-preserving isometries as in terms of a matrix Lie group, right? And it's almost a group of matrices, right? Almost, except that we have to factor plus minus the identity. Okay, so let's start with one. So, well, the point is that by definition of the Riemannian metric we have put on the upper half plane, the Cayley transformation is a Riemannian isometry. When we conjugate, when we conjugate our given Morris transformation that preserves D bijectively with phi. So when we do this, we go with phi, then we go with nu to D itself, right? And then we go back to U with phi inverse. When we do that, right, what we obtain is a Morris transformation that preserves U bijectively. So it is a Riemannian isometry of the upper half plane. But then we know that phi is a Riemannian isometry, so nu has to be a Riemannian isometry of D. Okay, so this proves one, and of course one can also be proved directly, right? Using the formula, using the explicit formula for the Riemannian metric on D. But okay. Now let's show two and take any Riemannian isometry of D, and I should have said here a orientation preserving. So here I should say maybe orientation preserving here. Okay, so this conjugation is an orientation preserving Riemannian isometry. So here I should have said orientation preserving, and here also should have said orientation preserving. But this means that this one is of the form Mobius transformation induced by an element of SL2R, which is what I say here. But then you see, now you can kind of pass this to the other side, right? And then use the fact that phi itself is a Mobius transformation to see that then C is you see is given by this Mobius transformation, where you conjugate this one by the Cayley matrix, right? Okay, and then and then kind of an easy juggling shows that that this one preserves D bijectively, and that's it, right? I mean, because that means that then one can ensure that this matrix is in SU11. Even though this one doesn't have determinant 1, right? Because when conjugating, I mean, this determinant cancels here, so you indeed get determinant 1. So okay. Right, and then well, 3 is an immediate, an obvious consequence of 1 and 2. Right? Okay, so as I said, as I said at the beginning of the class, we pretty much took the fact that we know we have computed things already in the upper half plane and kind of pulled everything through the Cayley transformation. That's very roughly speaking what we have just done. Okay, now the next thing, kind of a subtle point, which is we used the Cayley transformation to pull, in order to provide you with a Riemannian metric. What we did was we used this very specific transformation that sends you to D bijectively to pull GD to define GU. Right? But of course, we can ask, okay, how about using another Morris transformation, sending you to D bijectively, right? I mean, if we use any Morris transformation, sending you to D bijectively to pull the Riemannian metric on D to define a Riemannian metric on U, how do we know that we obtained the same Riemannian metric on U? In other words, if we don't, I mean, the Cayley transformation doesn't have to be a special one, right? So if it's not really special, then we obtain the same Riemannian metric on U if we use another Morris transformation? And the answer is we obtain the same, and it's the content of this corollary. So if you take any Morris transformation that sends U to D bijectively, then with respect to this Riemannian metric defined by the Cayley transformation, this nu is a Riemannian isometry, which is the same as saying that if we pull this one through nu, we obtained GU, right? So in other words, if we define a Riemannian metric for U using nu, we obtain the same one we obtained before. And this is again the same trick, quite easy, because if we use such a Morris transformation, we have U, we would have U, then D, which would be nu, and then we can compose, let's say, with the Cayley transformation inverse. I mean, with the inverse of the Cayley transformation, right? Inverse. And then this composition would preserve U bijectively. So, and it would be given by a Morris transformation. So we would know that it is a Riemannian isometry of this one, and then you cancel the inverse of the Cayley transformation, because that one by definition that it is a Riemannian isometry. So nu is a Riemannian isometry. Okay, so somehow this tells us you could have as well just used any Morris transformation sending U to D bijectively to pull the Riemannian metric, and you would have obtained the same. Okay. Now, how about computing explicitly the formulas for the correspondence rules of the Riemannian isometries of D, right? As we did in the upper half plane case, right? So take any Riemannian isometry. Now any Riemannian isometry, so it could be orientation preserving or not. So in other words, there's no adjective missing here. So, and then we have exactly one of the following situations. Either it preserves the orientation, in which case, well, we know the correspondence rule, that we know that the correspondence rule is given in terms of a matrix in SU11. Or otherwise, there is a matrix in SU11, so determinant 1, so there's no mistake there, with the property that the correspondence rule is given, in terms of this matrix, kind of as a Mobius transformation, but applied to the conjugate. And now here there is no minus here, and hence, also or in other words, we don't say here determinant -1. We don't say that because you see this reflection that we took in the upper half plane, which was which was given by sending any complex number z to minus z conjugate, which it's the reflection along the vertical, the imaginary axis. That one, when we pull that transformation to D, so you remember that here I said at the beginning of the class that the positive part of the imaginary axis was mapped to the open interval -1, 1, right? So the reflection along the vertical axis, the imaginary axis, is pulled or is sent, if you will, to the reflection along this one, right? So, which is just conjugating, right? So that's why this is that's pretty much why the rule is this one, without any minus sign, or which, in other words, without having to take anything of determinant -1. Okay, and I already pretty much told you how the proof goes. Okay, now some consequences, and actually some consequences, not even of this theorem, but actually, just from the fact that this specific isometry, the Cayley transformation, is a Mobius transformation, so preserves angles and sends circles to circles, and it's an isometry. So the shortest curves in D, well, to compute them, just compute the shortest curves in U and map them through the Cayley transformation, and what you obtain is, because of what we proved already for the upper half plane, is that the shortest curves in D are precisely the segments contained in the parts contained in D, or belonging to D, of circles in C bar that are perpendicular to the unit circle, which is the image of R bar under the Cayley transformation. And well, sometimes I like to use this notation, the circle at infinity, and also for R bar. Okay, so the proof of this theorem is pretty much Mobius transformations send circles in C bar to circles in C bar and preserve angles, and that's it. Right? And yeah, and the image of R bar under the Cayley transformation is S1, the unit circle. Okay, another theorem whose proof is pretty much the same. Is that we can compute explicitly the circles in the hyperbolic circles in D, and they happen to be precisely the circles of C bar that are contained in D. And this is because we know that in the upper half plane, the hyperbolic circles are precisely the circles in C bar contained in U. So, and the circles in C bar contained in U, where are they mapped to under the Cayley transformation? Well, precisely to the circles in C bar that are contained in D. So this theorem is also immediate. Of course, here something I'm not doing that maybe I can leave as an exercise is to compute explicitly the relation between the Euclidean center and the hyperbolic center of such a circle, which this we did in the upper half plane. Now I'm not doing it kind of just to see how you know, the fact that we did everything in the upper half plane allows us to go at least kind of to move forward, at least conceptually, right? Okay, so now again, mapping everything, mapping the facts that we established in the upper half plane to the Poincare disk through the Cayley transformation, we obtain a description of the geometric behavior of the let's say of the non-identity elements of the group of orientation preserving isometries of D, right? Namely, in the parabolic case, first of all, the unique fixed point of such an element of iso plus D, the fixed point as you know as a fixed point in C bar, it lies in the circle at infinity, or if you want, in the unit circle. Okay, that's just take what you know in this case for the upper half plane and map it through the Cayley transformation, and the kind of the horocycles, the circles contained in the closure tangent to the fixed point. So those horocycles, and by circles I mean the Euclidean circles, contained in topological closure of D and tangent to the unit circle at the fixed point. Those are invariant curves. So somehow the integral powers of my Mobius transformation, they move along. You know, somehow you can see iterating those powers. You can visualize them as kind of certain discrete flow, which can go like this, like, you know, counterclockwise or clockwise, right? So that both possibilities can happen. But of course, if you have here, let's say, clockwise, the motion is clockwise. It is kind of the flow is clockwise. Then it is clockwise everywhere, right? Okay, and also it is kind of it is kind of in a way kind of well ordered, in the sense that if I take a cross section by a shortest curve, since shortest curves go to shortest curves, the image is another shortest curve, which means that somehow, you know, here, if this point then would go to this one to this one, this one to this one. So somehow it is not completely like chaotic, kind of, that some points go like this, and like this point go to some point, and then this point go to this one, and then this point go to, etc. But kind of it's well ordered, right? Okay. Right. So here you can see that it's kind of, you see that these parabolic transformations in the unit in the Poincare disk, they look like something in between being kind of a rotation and a translation, right? Because this fixed point is not in D, right? It really doesn't belong to the plane, to the hyperbolic plane. Right? So these parabolic isometries, they look like something in between rotations and translations, like hyperbolic translations. Right? Okay, now let's move on to the hyperbolic case. In the hyperbolic case, well, from what we know in the upper half plane, we know now that if you take a hyperbolic element of iso plus d, its fixed points as a Mobius transformation from C bar to C bar lie both on the unit circle or the circle at infinity. Okay, and that the integral powers of that Mobius transformation look like certain discrete flow, kind of that is kind of repelled by one of the fixed points and attracted by the other fixed point. So let's say if this one is the repulsor and this other one is the attractor, somehow this sort of discrete flow given by the integral powers of the Mobius transformation then would move in this direction along the kind of the common circles to these ones, right? Well, the common circles, of course, the parts of the common circles that really lie, that are the segments of them that are contained in D, right? Okay, and also this flow given by the iterations of the Mobius transformation at any given point, they are kind of well ordered with respect to certain geodesics, which would be the following. So certain shortest curves, which would be the following. So take the two fixed points, and in C bar, consider the Apollonius circles of these 2 points. So those Apollonius circles, take the segments of those Apollonius circles contained in D, and then you see, since the unit circle is a common circle of the 2 fixed points, all the Apollonius circles are orthogonal to this one, which means by this theorem about the shortest curves, that these Apollonius circles, they really give me when I take their intersection with D, they are shortest curves. And what happens is that if I take one of those shortest curves, well, its image has to be another shortest curve, but in this case, well, I know that it's going to be another Apollonius circle. So this means that, for instance, if this point goes to this point, then this point goes to this one to this one, this one to this one, this one to this one, etc. So somehow I know that also that kind of the sort of discrete flow given by the integral powers of the Mobius transformation is kind of well ordered along these cross sections of the common circles given by the Apollonius circles of the 2 fixed points. So that's basically the behavior. And then, for instance, let's say, for instance, that the image of this shortest curve under my hyperbolic Mobius transformation is this other shortest curve. If that's the case, then notice, for instance, I'm saying in particular that this is repulsor and this is attractor. And then what happens is that the image of kind of this region is then this region, right? And that somehow this other region the complement of the original one I took, is kind of shrunk onto this one. Right? So you see somehow things are moved along, right? Are kind of pushed that way, right? And this would be easier to do. It would be easier to move my hands if I were in front of a chalkboard. But anyway, okay. So and finally the elliptic case. In that case, then again, pulling what we know in the upper half plane to the disk, to the Poincaré disk, using the Cayley transformation, what I obtained is that when I take my elliptic element of iso plus d and see it as a Mobius transformation from C bar to C bar, one fixed point lies inside the unit disk, and the other one lies outside the topological closure of the unit disk, so outside of the closed disk. But moreover, they are inverse points with respect to the origin and with respect to the center of this unit circle, which is the origin. Inverse. I mean, inverse not in the sense of Z inverse, but inverse in the set of this operation that that the inverse of a point, it's on the same straight line. You look for the unique point so that the product of this length with this length is the radius square, right? Which would be 1 in that sense, which is this operation, right? Kind of inverting in taking the multiplicative inverse, but then conjugating, because taking multiplicative inverse kind of takes you to the other side, so you conjugate to be on the correct straight line. Anyway, one of the fixed points, the relation between the two fixed points is that they are inverse in that sense. And then my elliptic Mobius transformation, it really looks like a rotation around that point, right? So a rotation, but of course now it's kind of in the hyperbolic sense, right? So that if you take a shortest curve passing through the fixed point, its image, it's another shortest curve also passing through the fixed point, right? And actually, you see the angle between a shortest curve and its image is actually the angle given by the multiplier, right? By the multiplier of the Mobius transformation. And when you iterate, and here maybe my picture is not perfect, but let's say that the image of this one is this one. Let's say that the image of this shortest curve segment is this shortest curve segment, and that the image of this second one is this one. Then my picture is not perfect, but actually this angle is equal to this angle, because it's given by the multiplier, given in terms of the multiplier, right? And this, and by the way, and this this circle, which would be an Apollonius circle of the two fixed points, this circle is actually, well, now we know it's a hyperbolic circle, but when you look at its center, it's precisely the fixed point, right? I mean, you can argue, for instance, the image of this point is this point, and this distance is equal to this distance, right? So at least the image of this guy, they are kind of all in a circle with the center, right? I mean the orbit. Okay, and then the rest of the argument to see that this Apollonius circle of the, which is an Apollonius circle of the two fixed points, is actually a circle with this center. The rest of the argument I leave it to you. Okay, so that's basically the behavior. Okay, and now let's wrap up a couple of things, right? So you see, we started our study of the three models with the hyperboloid. We saw that SO21M, the restricted Lorentz group, is contained in the group of orientation-preserving isometries of the hyperboloid, right? And that the orthochronous Lorentz group is contained in the group of isometries, orientation-preserving and non-orientation-preserving. Okay, then we moved on to the upper half plane, and in the upper half plane we were able to compute the full group of orientation-preserving isometries as PSL2R. Kind of something that we were not able to do in the hyperboloid. In the upper half plane, we were able to do it, and we were also able to compute the full group of isometries of the upper half plane as a certain semi-direct product, a certain very concrete semi-direct product of PSL2R with the two-element group. And actually, we saw that as a quotient of a matrix Lie group is this PS star L2R. So we were able to fully, to give us the full concrete realization of or description of the isometry group. And then in today we used that to give this full description of where is it? Well, this one, yeah. Well, okay, so. Okay, so let us wrap things up and see that in the hyperboloid we have actually computed the full groups of isometries, the kind of the orientation preserving isometries and the full group of isometries, orientation preserving and non-orientation preserving. To do that, let's first show kind of a technical lemma in the Poincare Disc, which says that if you give me a Riemannian isometry of D that fixes 0, and with the property that its derivative in that point happens to be the identity in the level of tangent plane, then it's the identity transformation, right? So we know that the identity satisfies this and this, right? That the identity function of D satisfies this condition, and what I'm saying is that it's the only isometry that satisfies those conditions. Okay, so let's prove that. So you see, so I mean, this lemma you can interpret it as saying that somehow these local conditions determine the isometry globally, if you will. Okay, so first of all, if you give me such a nu satisfying these two conditions, it has to preserve orientation. Well, why? Pretty much, you see that the determinant of this one it has to be positive. So having the positive determinant at one point, it has to have positive determinant everywhere. Okay, so it has to be orientation preserving, so it has to be given as the Mobius transformation of an element of SU11. Okay, and now this allows us to compute things explicitly, because since it fixes 0, beta has to be 0. This is obvious. And now, so here we have this 0, because here we know that it's the conjugate. So now we only have to deal with this alpha, which you see at this point, we know that alpha times alpha conjugate is equal to 1. So at this point, what we know is that alpha lies on the unit circle, right? But we want it to be 1 or minus 1. Okay, now the derivative is multiplication by this complex number. I mean, you just compute the derivative. We already did some time ago. You compute the derivative knowing, as a map of a complex variable, right? Like that. Nu is a map that goes from D to D. So, well, I mean, yeah, mu A. So it's given by this one, by the usual quotient rule for derivatives. Okay, so what you obtain is pretty much this part. But we know that this is the identity, so this number has to be 1. Right? So this has to be 1. So alpha conjugate has to be 1 or minus 1. Right? So here, when I look at here, I know then that, I mean, being 1 or minus 1, it's equal to alpha. And so I can deduce that that A is plus or minus the identity, so nu is the identity. Okay, so you see this lemma, what it tells me is, you see, if some isometry fixes 0 and you know something about its derivative, then you know a lot about that it is given as a Mobius transformation, and you know a lot, right, globally. And you see these conditions, both the hypothesis and the conclusion, when you apply the stereographic projection from V to the hyperboloid, you see this one 0 goes to n, to 0, 0, 1, right? The identity has to go to the identity. The derivative goes to the derivative, and the identity isometry goes to the identity isometry. So so this lemma that we have just proved remains true for the hyperboloid. Okay, and now this is what it will allow us to prove that from the very beginning we had already computed the whole group and the whole group. So let's prove it. We already know. I mean, this we showed. This is one of the first things we showed. These containments, these inclusions. And now take any orientation preserving isometry of M. Then I leave you as an exercise to see that there is an element in the restricted Lorentz group that sends 001 to this point. This, for instance, this we know because we showed that the action of this one of this group on the hyperboloid is transitive, right? So this we know. But furthermore, I claim that this, once you have this property, you can kind of keep tweaking A little bit in such a way so that its derivative at this point is precisely the derivative of phi. And here, what I mean is the derivative of A. I mean the derivative of the linear map multiplication by A. And I leave you to think why. Okay, but the thing is, you see, once you know this, then you apply the chain rule, and you see that when you consider this composition, you see this composition satisfies satisfies the hypothesis of this lemma, but for the hyperboloid. So it has to be the identity of the hyperboloid. So the identity of the hyperboloid, but this means that A is equal to phi because both are bijective. Which means that every element here is an element here, and then we have this equality, right? And then I will leave you as an exercise to show this other this other equality. So let me write it. Exercise 72. Show that and this would finish the proof. Okay, and that's it for today.